All right, folks, one last section for the semester. I'll be done. Uh-oh, I didn't even know. What the heck? That's okay. Polar coordinates, something like this. Suppose we have XY system like this, a Cartesian coordinate system. Typically, we pick a point and say, hey, the coordinates of that point are x comma y, right? If I say 2 comma 3, what that means is you go to x equals 2 and y equals 3 and you plot up, you pick that point, and that's where you have 2, 3. But in fact, we can represent this using what's called a polar coordinates also, a point as polar coordinates. The idea there being, if I say for example, 1 comma pi fourths, that means at a distance of 1 from the origin, and pi fourths is the angle from the positive x-axis. So you have to go counterclockwise pi fourths, which is 45 degrees. And from the pole, what is called the pole axis, the origin, you just go to a distance of 1. So r sort of represents the distance and theta is this angle. All right. Uh, that that word distance is kind of used a tad loosely here, because in polar coordinates it's entirely possible to have a negative value for r. Okay, what would that mean? I'll show you what a negative value for r actually means. Okay, and so one more thing, yeah. um, Given r theta, let's focus on this one. Given r theta, to find the corresponding xy coordinates, right? You know the polar coordinates. Can you find the corresponding xy, the Cartesian coordinates? Yeah, simple. X equals r cosine theta, you say. Y equals r sine theta. Where did that come from? And if I were to drop a perpendicular onto this, we have a right triangle, and from trigonometry, then this y would be y over r is sine theta, so y equals r sine theta. Similarly, x over r is cosine theta, so x equals r cosine theta. That's where it came from. Or if you're given x and y, can you find r and theta? Yeah, the relationship is r square is x square plus y square, and tangent theta is y over x. Now I want you to pay attention to something that I'm about to say here. Notice how I'm not saying r equals square root of x square plus y square. Rather, I'm leaving it as r square is x square plus y square. That's because it's possible for r to be chosen to be a negative value. Okay, and also I'm not saying theta is tan inverse of y over x, and instead saying tangent theta equals y over x. And that's because when we say theta is tan inverse of y over x, tan inverse will put you only in the fourth or the first quadrants. Tan inverse of a number must be either in the fourth quadrant or in the first quadrant. However, it's entirely possible that theta could be in the second or third quadrants. What about those things? That's why we simply say tangent theta is y over x. That's it. Okay. With that, let me move to GeoGebra and show you how to plot a whole bunch of points. Boy, that graph looks a little busy, right? But look at what I'm trying to show you there. I drew three different circles of radius 1, 2, and 3 respectively. And we have this traditional XY. And at pi over 6, which is 30 degrees, I drew one line segment. Another one at 45 degrees, 60 degrees, 90 degrees. And then 120, 135, and 150. Yeah, 150, right? And similarly, add 30 to this 180, 210, add 45, 225, add 60, 240. All these different angles, I drew these things. Our intention is to plot a whole bunch of points, which ones these A through I that I have listed here. So if I want to plot 1 and pi fourths, what should I do? Well, I should go to the radius of 1, right? That would be at a distance, that circle, every point on that circle is at a distance of 1. So I should go to that radius, and also I need to pick this pi fourth line, that segment, right? So that A would be that point. Would you agree with me? Is it on, we need to draw 1 and pi fourths, right? So is that point on the pi fourths angle from the positive x-axis? Yes. And is it at a distance of 1 unit from the origin? Yes. That's it. Okay. What about B, which is 2 comma pi sixths? Which angle we should go to? Pi sixth, this guy, the 30-degree guy. At what distance? At 2. Would you agree that's the point? Yep, that's B. 3 and pi thirds? 3 and pi thirds should be that, right? Uh, 2 and pi halves, right? That guy. Uh, E. E is 1 and 5 pi 6. 1 and 5 pi 6. There we go. Now the question is, what if we have 2 and negative pi 6? Oh, negative pi 6 is, you just go clockwise from the positive x-axis at an angle of pi 6. Pi 6 is 30 degrees. So you go 30 degrees. So that's this guy. And what's the radius? What's the R value? Oh, 2. So that means we should get this point. And there we go. F is 2 and negative pi 6. Now G happens to be 2 and 11 pi 6. Okay, let's go to 11 pi 6 angle, which is this guy, and 2. Wait a minute. Well, that was F, right? 2 and negative pi 6 was this guy. How, you mean 2 and 11 pi 6 is exactly the same? Yep. So that is what is a tad bit weird about polar coordinates. The very same point can be represented in more than one ways. I can call this as 2 negative pi 6, or I can call this point as 2 11 pi over 6. Can you think of any other ones? Yeah, what if we just went full circle again and came back to this point? So that means to 11 pi 6 add a 2 pi. Yep, that would work. What about 4 pi? That means twice you go around the circle and come to this point. Yeah, that's also, you can represent this point with that angle as well. So a single point in polar coordinates, uh, a single point can be represented in multiple ways in polar coordinates. But that's not what happens in Cartesian coordinate system. When I say 3, 4, that represents a point uniquely. There is no other way to write 3, 4 in Cartesian. Not so in polar. That's one of the main points. Okay, with that, let's look at this negative 1 and pi 6. R is negative? Yeah, R is negative. That's perfectly possible. Okay, how do we plot that? Oh, the angle is pi 6. So we go to pi 6. But because it is negative 1, we don't go to this side, we go to the opposite side of, you extend this pi 6 line into the opposite quadrant. There you go to a distance of 1, which brings you to this point. Did you follow that? To get negative 1 pi 6, you initially go towards pi 6, but then you go in the opposite direction of pi 6 into the opposite quadrant and go to a distance of positive 1 unit there in the opposite quadrant. So that's your negative 1 pi 6. Similarly, negative 2 pi thirds, go to positive pi thirds, but go to the opposite quadrant. Negative 2 should be somewhere over here, this point, right? This is how you plot points, folks. All right, and now let's see. Whoops. No, don't save. What if, yeah, I got this one here. What if we needed to draw a polar curve? Now that we have learned how to draw a whole bunch of polar points, can we draw a polar curve? What's a polar curve? A polar curve is of the form r equals f of theta, a less than or equal to theta, less than or equal to b. That means theta lies between a and b. Let me pick a simple example. R equals 1 plus cosine theta. Okay, so 0 less than or equal to theta, less than or equal to 2 pi. Again, I prefer to just go ahead and use GeoGebra. Makes life simple. For that, notice something. Have I mentioned earlier that x is nothing but r cosine theta, y is r sine theta, right? How you go from polar, given polar, r and theta, how do you find x and y, the Cartesian? X equals r cosine theta, y equals r sine theta. So that means if you are required to draw r equals f of theta, that means x is nothing but f of theta cosine theta, right? I'm replacing r with an f of theta. And y is f of theta sine theta. X equals f of theta cosine theta, y equals f of theta sine theta. Does that remind you, that kind of form, does that remind you of something? Doesn't it look like some kind of a x equals f of t and y equals g of t, the parametric curve? Yep. So the parameter happens to be theta here instead of t. So we can draw polar curves using by thinking of these things as parametric curves with the parameter being theta. Well, you call it theta or t, doesn't matter. So if your objective is to draw this r equals 1 plus cosine theta 0 less than or equal to 2, this is what we do. First you say f of x equals 1 plus cosine x, right? And a equals curve of f of t times cosine of t, comma f of t times sine of t, t0 2 pi. This you should be familiar with because it's exactly the same command that we issued for a parametric curve. Cool. So let me show that. Let me go to GeoGebra and illustrate this with an example. Okay, f of x equals 1 plus cosine of x. So we got that curve, and then we'll say a equals curve f of t times cosine t. Be sure to do that. F of t times cosine t, comma f of t times sine of t, comma t, comma 0, comma 2 pi. 2 pi, 2 pi, Sammy. And we got the graph. So I'm going to toggle the visibility of f of x. I don't need that graph. And here is the polar curve. Cool. I'll turn off the label. And ladies and gentlemen, Here is the polar curve. That's it. So if you happen to, when you go to calculus 3, you will be required to do parametric curves for 3 dimensions. My suggestion is just go ahead and use GeoGebra even for that. GeoGebra has 3D stuff that you can do, and it'll make your life very simple. All right, folks. Was there anything else that I need? Did I do some? Uh, yeah. Polar graphs of sines and cosines. Yep. Let me show you some stuff that I did. For example, you want say uh, r equals sine theta. Okay, r equals sine theta. So check this out. R equals sine theta would simply be a circle with the origin located at 0.5, 0.5, and the radius is 1/2. Okay, and r equals cosine theta would once again be a circle located like that. Okay, and sine of 2x would have 4 lobes like that. Look at the orientation of sine of 2 theta. Sine of no, cosine of 2x or cosine of 2 theta instead would look like that. Okay, so let me turn. So this is cosine of 2 theta in polar graph, whereas this is sine of 2 theta. And put them together, that's a pretty looking one, right? All right, few more. What if we have sine of 3x? Well, that has only 3 lobes. Cosine of 3x? I'm sure you guessed it. Yep, 3 lobes like that. Sine of 4x has 8 lobes. Cosine will also have 8 lobes. Okay, so you can play around with this. That's the beauty of it. Dang, that looks pretty, right? And I think I have some more ones. Ah, 1 minus sine theta. That's how the graph looks like. 1 plus sine theta looks like that. And put them together, looks like this. That's pretty too. Okay, 1 minus cosine x. Like that. 1 plus cosine x. Or 1 plus cosine theta, I should say. Looks like this. All right, folks. Okay. So, ladies and gentlemen, I am done with this course. So, I enjoyed having you as students, and I wish you all the best.